So let us start, or rather let's continue what we did last time. Yes, sure. So we stopped at the proof of the fact that if our basic group G is compact, then the dual group is discrete, and for that we need the notion of the Fourier transform. So I remind you that there is a one-to-one correspondence between characters and continuous characters. And continuous, non-zero continuous linear multiplicative functionals. So the set of continuous linear multiplicative functionals was denoted by M of G. This is a Gelfand space of G. Space of L1 of G was a spectrum. So the Gelfand transform of F in 1 of G is a function f, say, tilde on M of G well, in particular, this of tilde is continuous. Now, in our case, this space is identified with the space of characters, and we know that this space of characters, it is denoted by gamma. It is a group and a topological space. And the topology is the same as on the Gelfand space. It is a weak topology of the conjugate space to L1. And so this Gelfand transform turns into what is called the Fourier transform. It is quite usual to denote this by, well, let's write this way, by f hat of gamma. So this is a standard notation for the Fourier transform, and in our case it simply the same as the Gelfand transform, none other than, and well, okay, so it arises as the Gelfand transform for the algebra L1 right now.
Maybe there should be small f.
Sorry?
In the middle of the form, phi small f.
Small f, okay. Okay, so anyway, this is a continuous function on this dual group, simply because this is the same as the Gelfand transform, and the topology of the dual group is the Gelfand topology, so this is continuous function. And after that, our claim about the fact that gamma is discrete if G is compact is very easy, because simply let G be compact and take the function 1. It belongs to L1 in this case, because the Haar measure is finite. And so consider its Fourier transform, and of gamma, and it is equal to 1 if gamma is equal to 0, and to 0 otherwise. So last time we finished with the proof that the integral of any character which is not identically 1 is equal to 0. So we have this, and when is gamma is equal to 0, that is it is a function identically equal to 1. Then surely we have this. And so we obtain that this function is continuous on the dual group. And since it's continuous, 0 is an isolated point of the dual group, and since all shifts are continuous, it's quite easy to see that all shifts are continuous. It follows that all points are isolated, or otherwise you simply can consider the Fourier transform of some character, and you obtain a function which is 1 at this character and 0 otherwise. So all points are isolated, and then the group is discrete. Okay. Well, now probably it was doing the following thing. It was to understand what the characterize the case of some very classical groups. I think you know this, but still it is good to repeat this. Even if you know, let's repeat. So let's first G be equal to R, which is a group under addition, under the usual addition. So it is a locally compact topological group, and what is gamma? Yes, sure, you know. I know that you know. But maybe all of you know, but still I want to repeat the argument. So consider continuous character, that gamma be a continuous character. On R, then gamma of x plus y is equal to gamma of x, gamma of y. Then we take some function u, say in c infinity of r, multiply this by u and by u of I, u of y, and integrate. So, well, and before that, probably it is good to replace y by minus y. So if you write this way, then we should put bar here. Okay. So let's multiply this by u of y, integrate, and then we obtain the following thing, that the convolution, well, the integral over r of gamma x minus y u of I is equal to gamma of x, well, dy is equal to gamma of x, the integral, well, simply u hat of, no, let's write this as an integral. Okay. Now gamma is a non-zero, a function in L infinity equal to 1 almost everywhere in modulus. So we can find u so that this function is this integral is non-zero, should, because gamma is a non-zero, non-trivial infinity function. So on some function in this C infinity 0, well, sorry, the Schwarz class, some C infinity function with complex support, then all these integrals exist, and we may choose this function u so that this integral is non-zero, and then we see that gamma is a quotient of these two functions. This function over this number, of this quantity, and this function is infinitely differentiable, because you can write this convolution in the opposite way just by changing the variables, and then we see that the differentiability properties of u pass to this convolution, so this is infinitely differentiable. So the conclusion is that gamma is infinitely differentiable. Okay? Well, and as long as we know that gamma is infinitely differentiable, we write again the basic relation. And differentiate it, say in x. So gamma prime of x plus y is equal to gamma prime of x, gamma of y. And this is true for all x and y. And now we put here y equal to minus x. And this guy is equal to 1 in modulus everywhere. So this is something, well, okay. So what we have here, so when y is equal to minus x, we obtain gamma of x bar here, and then we divide. So gamma of x is equal to c gamma prime, well, okay, gamma prime of x is equal to c gamma of x, where c is this thing, gamma prime of 0. Well, gamma prime of 0. And now we see here the differential equation for the exponential function. Then it follows that gamma of x is equal to a times e to the power cx. Okay. Now at x equal to 0 we must have 1. So a is equal to 1. And also this function must have modulus equal to 1 everywhere. So c is purely imaginary. So there is alpha real such that gamma of x is equal to e to the power e alpha x. So these are all characters of the group R. And so they are in one-to-one correspondence with real numbers. These are different functions if alphas are different, so gamma is equal to R this way. And then it is natural to write the Fourier transform as a function on R instead of a function on the set of characters. So on R, f hat of alpha is equal to the integral over R of f of x e to the power minus I alpha x dx, and minus is because in the definition of the Fourier transform I use bar. Okay. Now the next theorem, which is usually from this point, of course, you all know. The next theorem, which is usually proved about Fourier transforms, which is do you remember? After that. No. Before, quite elementary thing. So it's claimed that this function is continuous, which is. Also, it is claimed that it tends to 0 when alpha tends to infinity. This is Riemann-Lebesgue theorem. Yes. Yes. Riemann-Lebesgue theorem. It tends to 0 when alpha tends to infinity. Well. So, do you remember how this is done? Yes, so this is done in the following way. First, we suppose that f is smooth and has compact support. Then, by integration by parts, we easily deduce that this is true in this case. And then we approximate an arbitrary function by a smooth function with compact support, and so on. The point is that the Riemann-Lebesgue theorem is also true on every compact abelian group. So the Fourier transform of every function in L1 tends to infinity at infinity. Why? This is not because of approximation by a smooth function, because there is no smooth structure, but why? You know. In fact, you know. Why the Riemann-Lebesgue theorem is true for every compact abelian group, locally compact abelian group G. Why is it true? You know, in fact. And this is immediate. But not in this way by approximation, of course. Well, you remember what M of L1 of G is. This is the Gelfand space. The Gelfand space of the algebra of L1 of G under convolution. So normally this algebra has no unity. If it has no unity, we add this unity artificially. And then there arises some distinguished continuous linear functional. So it takes f beta to beta. Yes. So it takes the Gelfand space, the spectrum of the algebra of such pairs. Then we consider this distinguished continuous linear functional, all functions of the initial algebra, all functions of this sort, they vanish at this functional, at this distinguished functional. So this functional is equal to 0 on every function in the initial algebra. Sure, because here we have 0. Yes? The spectrum of L1 of G consists of all continuous linear multiplicative functionals which are not equal to this one, all other continuous linear multiplicative functionals. And if we adjoin this distinguished functional, we obtain a compact space. So all functions of the form f hat, they live on this compact space. They are continuous on this compact space, and they are 0 at this distinguished functional, at this point at infinity. Yes? So if you remove it, what happens? They will tend to 0 when the point leaves wider and wider compact sets. Okay? So this follows from the Gelfand theory, not from approximation, not from this trick, from the Gelfand theory. So in particular, this is by transfinite induction, because Gelfand theory involves Zorn lemma, and by some complex analysis, because the Gelfand theory involves Plancherel, no, not Plancherel. Liouville theorem that every bounded entire function is constant. So Gelfand theory involves that. Well, so this Riemann-Lebesgue theorem in the general case, this is a consequence of some fairly non-easy things, but otherwise it is immediate. You need not approximate anything by something smooth and so on. It is immediate, though highly non-constructive. Okay. Now, what else can be said? If our group is the unit circle on the multiplication, then also you know what the characters are, and this can easily be proved. So if you have a character, let gamma be a character of T, then there is a canonical mapping of R onto T, let it be psi. Okay. And then gamma of psi, the composition of gamma and psi is a character of R. Okay, so this is a character of R, and so it has, this function has this form, but it must be 2 pi periodic. And then it follows that it is of the form e to the power this. Okay, no, this is one periodic. So. Okay, this way. What I wrote, this is one periodic, and this is 2 pi periodic. Okay.
Yes, it depends on which. Yes.
Well, but this is 2 pi periodic. This is 2 pi periodic. So if we consider this composition. But anyway, all characters are such, and so the Fourier transform is simply the sequence of Fourier coefficients, and so this group gamma is discrete as follows from the general theory, but so that is discrete, of course. And also we have here the Riemann-Lebesgue theorem, the Fourier coefficients of any integrable functions tend to 0, and again this follows from Sorgen theory in our setting, not because of some approximation. And also maybe when G is equal, so here gamma is equal to Z, okay? At least it can be identified with Z. And if G is equal to Z, so let gamma be a character, then so it is Z under addition, but also we have the unit under multiplication, and well, if we take this gamma of 1, let it be it's the point of the unit circle, surely. This is the point of the unit circle. So this is of the form e to the power I theta. Yes? And it follows that gamma of n is equal to e to the power I n theta, just because this function is multiplicative. Well, the basic property of the characters implies that this is true. So all characters of Z are determined by points of the unit circle. So, okay. So in this case, it's everything.
But it somehow seems that there is like a one-to-one correspondence.
Yes, sure. Well, if you take the group of character of gamma, you obtain again G, always, but this is not evident.
Yeah,
this is not evident, and we shall prove it. But to do this, we need some preparations. Well, I cannot pass to this during this lecture. Even. So here, in these examples, the dual of R is also R, and because of this duality form, we see that vice versa. And also the same with the unit circle and the group of integers. Duality formula shows that this is a bilateral correspondence, and the point is that this is true for every locally compact abelian group, but to prove this we need some work. And so what I'm doing now is just to do this work and to see that.
So this lecture?
Sorry?
Will we prove this fact in this semester?
Not during this lecture. Simply, we should prove many other things before we do this. Well, somehow we must prove the inversion formula for the Fourier transform. You know, let me just describe what will happen. So we must recover the inversion formula for the Fourier transform in the general setting, and on R, say, To prove the inversion formula, we use again smooth functions, Schwarz functions, something like that. Yes, and when we use it, then everything is clear. On a general group, we have known the separators, of course, and even we don't know many other things. We don't know whether the characters separate the points of the group G, whether there are sufficiently many characters, whether there is a uniqueness theorem, for example. If the Fourier transform of some function is equal to 0, is it true that this function is equal to 0? So from the outset, this is quite unclear. Well, and so we shall prove this, but to do this, some work is required. Even we don't know if gamma is a topological group with this topology, this Gelfand topology, for the moment. So it is a group on one hand, and it is a topological space on the other, which is locally compact. But whether these two structures are compatible, it is not known.
The question is whether the multiplication
is continuous, yes. Whether the multiplication is continuous, well, this is not quite difficult, but still it needs, some proof is needed. So there are many tiny things which should be understood before. Okay. Now let's advance step by step. Consider the following thing: the space A of gamma. This is the space of all Fourier transforms. What do we know about this space? First, this is an algebra. Is it clear? Because this is obtained by Gelfand transform. So Gelfand transform takes any function, any Banach algebra, any commutative Banach algebra to some algebra of functions. It's an algebra. Also it embeds in the space C0 of gamma. What is C0? C0 is the set of functions that tend to 0 at infinity. If gamma is compact, this coincides with C on gamma, and otherwise these are functions that tend to 0 to infinity. So this is the Riemann-Lebesgue theorem which I explained. Okay, all this. So next, let this symbol I don't know, maybe it is worth writing 3 vertical lines. This is by definition the norm of f hat in C0 of gamma, and this is the spectral norm. spectral norm of F. Again, this is a general notion. When we have an arbitrary commutative Banach algebra, there's a spectral norm of any function in this algebra is the norm of its Gelfand transform in the uniform norm of its Gelfand transform. Then next A of gamma separates points of gamma. If there are two non-equal points of gamma, then there is a function f in L1, so that the Fourier transforms of this function, Fourier transform of this function takes non-equal values at these points. This is simply because, again, by definition and by the Gelfand theory, so what are the points of gamma? So these are characters, but at the same time, they correspond to continuous multiplicative functionals on L1 under convolution. And so if two such functionals coincide on all functions in L1, then they must coincide. So if they are different, then they must differ on some function in L1. So this is, again, a triviality. What is non-trivial, that this algebra is self-adjoint. Non-trivial in the following sense: it is simple here, but this is not a general property of Gelfand transforms. So if you take a commutative Banach algebra and take the space of Gelfand transforms of functions in this algebra, then this new algebra is not necessarily self-adjoint in general. But this one is self-adjoint, and so consider function f in L1 of G, and consider also the function of this sort G of x is equal to f of minus x bar. Then if we take the Fourier transform of this function G, what do we obtain? This is the integral of f bar of minus x gamma of x over the Haar measure. Then I can replace x by minus x. Gamma bar. I can replace x by minus x, so I can do this way, and this is the same. Then I can erase this minus and this bar, and after that I obtain f hat of gamma bar. So with every function, this algebra contains its complex conjugate. Consequently, A of gamma is dense in C0 of gamma by the Stone-Weierstrass theorem. So you know a version of the Stone-Weierstrass theorem for compact spaces, but for the locally compact, this is precisely as you encounter here. So if you have a separating subalgebra of this algebra, then it is dense, self-adjoint. Separating self-adjoint subalgebra, it is dense.
I just remind how to prove it.
The proof is that you simply adjoin the unity. Infinity, yes, and apply the Stone-Weierstrass theorem to this setting. Then, Yes, 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 yes.
Also
Yeah.
separate the infinity.
Yes, yes, but so the statement of the Stone-Weierstrass theorem is that if you have a space C on K, where K is compact, and if you have a subalgebra of the space which separates the point, is self-adjoint, and also separate every point from zero, then it is dense. If we lift this last condition, that not all points are separated, then there is precisely one point at which all functions in the closure vanish. And here, this only point will be the point at infinity. So, so just in this way. Okay. Next, A is translation invariant and is invariant under multiplication by characters. Well, these are also basic properties of the Fourier transform, which you know from the case of R and from the case of Fourier coefficients. Here the proofs are nearly the same. Well, I show that. Well, so to do this, first let's calculate the Fourier transform of a shift of our function f. So let f be in L1 of G, and consider fy. Then fy hat of gamma is equal to the integral over G of f of x minus y gamma bar of x dx. And if we introduce this new variable and use the invariance of our measure, so this is equal to the integral over G of f of, say, s gamma bar of s plus y ds, and this is equal to gamma y bar f hat of gamma. Okay, so we see here that this transform is multiplied by a character, not precisely by the character gamma, but well, by characters. What I mean here by characters, a character is a function on G, and here I must multiply. I still multiply by something like that. But as a function of y. So when I say that it is stable at the multiplication by characters, I mean that it is stable at multiplication by such functions on gamma, you know. And this calculation proves this. We have bar here, but this doesn't matter because we can put start with gamma bar and so on. Okay. Well, this is first thing, and the second thing, to obtain translation invariance, we should calculate the Fourier transform of the following function. So let again f be in L1, and consider gamma f hat, well, not gamma, probably rho. So let rho be another character. Consider this thing. This is equal to the integral of g over g of f of x, rho of x, gamma of x bar, and this is the integral over g of f of x, gamma rho bar of x, and this is, if you pass from multiplicative notation to additive, this is precisely in the group gamma, this is the difference of gamma minus rho. Sure. Well, here there is some ambiguity because characters are added multiplicatively. When we add them in the group gamma, we should multiply them as functions. So here we have this function. As a function, this is the product, but as an element of the group gamma, this is the difference. Okay, so this is equal to f hat of gamma minus rho. So this is what we call f hat rho of gamma. Okay. What else should I? What else should I? Claim. Well, I don't remember, but okay, let's pass further, and if we need something, we'll prove it immediately. But I don't remember what simple properties should I list. Anyway, these properties on this level, they are all these simple properties are all basically of the same level. So all of this is not very interesting, but. Now we want to prove that in fact gamma is a topological group. Under the Gelfand topology. To prove this, we need to show some basis of neighborhoods of unity in the group gamma and also in the group G. So the proof needs some preparation, and these preparations will be used also in some other arguments further. But so what I am going to show you now is a little bit more than it is required for proving precisely this fact. Okay, so preparations. Consider some compact set K in G, and consider the set, how to denote it, U K epsilon. epsilon will be a small positive number. This is a subset of gamma, and it is defined in the following way. U k epsilon is the set of all characters gamma in this group capital gamma, such that okay. Now let me check if I am correct. Next, let us do something which seems to be dual to this. So let's exchange the roles of gamma and G. Let now C be a compact subset in gamma. Consider the set V, C epsilon. This is the set of all x in G, for which we have the same. So each compact subset in each of these two groups generates some set in the other group. So if we have a compact subset here, we obtain a set U in the group gamma in this way, and this is totally symmetric, but with the roles of the groups exchanged. What then? First, this set UK epsilon is open in gamma, and this set V C epsilon is open in G. So these are open sets. So that they are open neighborhoods of unity, because surely the unit character satisfies this. Estimated also here. The unit element satisfies this estimate. Second, the sets U K epsilon form a base of neighborhoods of unity in gamma. Later we shall see that symmetrically this family of sets also forms a base of neighborhoods of unity in G, but right now we cannot do this precisely because we even don't know if there are sufficiently many characters. So in principle this family it is allowed to be very, very thin. For the moment, we don't know if it is sufficient for determining the topology, because simply, maybe there are not so many characters and so Okay. Well, and to prove these two facts, well, we need the following thing, okay, so lemma. So this function of two variables is a continuous mapping of G cross gamma to the complex number. So to the unit circle, that's the same because all values lie in the unit circle. So we know that this is continuous separately, of course. This is continuous in X because every character is continuous, and this is continuous in gamma when X is fixed because we have Gelfand topology. So okay. So anyway. Well, maybe about gamma this is not so much clear. About X, this is clear at least. That this is continuous in X, it is quite clear. About gamma, probably not so much because, well, I referred to the Gelfand topology, but this is related to gamma as a function on L1, on the space L1. And not on, well, okay. When some net of gammas tends somewhere, then its values in L1 also tend to an appropriate number, but it is not clear what happens with this. So this is not a function L1. So even this is not quite clear, maybe. But the lemma claims that, in fact, this function is continuous as a function of two variables. And for that, well, what should I erase? For that, we simply use the formula which was already on the blackboard. So it was this way, it seems to me. Well, it was this way. Now we use this formula, and again. So if gamma is some character, then surely there is a function f in L1, so that if height of gamma is not equal to 0, well, then this function is also not equal to 0 in some neighborhood of gamma. So in some neighborhood of gamma, this thing is equal to gamma of x is equal to fx hat of gamma bar over f hat of gamma. This is continuous in gamma. And so it turns out that we must, also here we have bar. We must prove that this function is continuous as a function of two variables. Okay? So if you prove that this function is continuous as a function of two variables, then we prove the lemma. Okay? Okay, so sorry?
Could you please repeat what did you say about
we need this so we need this function, yes? We need this function. We must prove its continuity. We want to represent it from this formula. To represent it from this formula, at least we need that this factor shouldn't be equal to 0. But since we deal with the dual group, so gamma corresponds to multiplicative linear functional, continuous multiplicative linear functional, then this functional at non-zero, of course. All such functions are non-zero. All points of the Gelfand space are non-zero functionals. Yes. And since it is non-zero, there is a function f for which this guy is non-zero. And this guy is a continuous function on the group gamma, again by Gelfand theory. So it is non-zero in some neighborhood of this point gamma. And then in some neighborhood of this point gamma, we can write this representation. After that, we see that it remains only to prove that this guy is continuous as a function of two variables. Okay. And to do this, we simply use the fact that the spectral norm is dominated by the usual norm of a function. This is again something commonplace of the Gelfand theory. The spectral norm is smaller. Okay, so we need something like that. So we need fx hat of gamma minus fy of delta also hat. We need this thing, so this is equal to f hat x of gamma minus f hat y of gamma plus f hat y of gamma minus f hat y of delta. Okay, after that we take the absolute values. well, probably, well, what I did, probably not quite good, probably not very correct. Well, because, okay. Not quite convenient, let me say. Not quite convenient. It would be better. If this can be corrected, let me do this in a slightly different way. Fx, well, fx by fx of delta, and then fx of delta minus fy of delta. Let me do this way, maybe. No, not quite the same. I subtract. Well, I change here this parameter.
Yeah, but it's the same if you change x to y and y to x.
Yes. But somehow what I am busy with, I have point x gamma, and I want to. Well, let's fix the point of view. I have some point x gamma, and I want to check the continuity of this function at this point. So x gamma is some fixed point, and y delta is some variable point. So let's write in this way. Then, there will be fx of gamma minus f hat x of delta, and here it will be fx minus f y hat of delta. Okay. Well, and after that we estimate it this way. For n delta, this guy does not exceed the spectral, so the spectral norm of this function, and the spectral norm doesn't exceed the L1 norm. Okay. And after this, the required continuity is clear, because we know that when y tends to x, this shift tends to this one in L1, and here x is not changed, so only this character is changed, and so the required continuity falls simply by the continuity of the function f hat, fx hat, and so on. Okay. Well, so now let us show that are open in G. Of course, we shall use this bicontinuity of this function gamma of x to do this. And the other claim that all sets C, V, C epsilon are open, well, not in G, but in gamma. The other series of sets is open, consists of open sets in G. So this is proved in the same way, precisely in the same way as this claim. So I'll skip that proof, but I show this one. Okay? Well, now what it is, U, K, epsilon. This is a set of all gamma in.
This is just a two lemma.
Sorry?
Two lemma in
the first was proposition probably, so something about this sets UK epsilon, the sets V, C epsilon, so I must prove that they are open first, and that these sets form a basis of neighborhoods of unity in the group gamma. Okay? Well, so I split this in small portions, and one small portion is that these sets are open. Well, to prove that the sets, they're sister sets, brother sets, V, C, epsilon are open in G. The same argument applies. So this is the argument is the same. So I show only this. It will be clear how to change everything. So the set of all gamma in gamma, for which gamma of x minus 1 is smaller than epsilon for all x in K. And I remind you that K is a compact subset of G. Okay. Now, this function is continuous in two variables. So if gamma 0 is in this set and x0 is in K, then we have this inequality. And so the same inequality is preserved at nearby points. By the lemma, there exists, how to denote it, let it be V, a neighborhood of gamma 0 and W neighborhood of what? Let it be of x0, of x0. So this is a neighborhood in G. So that this thing, gamma of x minus 1, is still smaller than epsilon for every gamma in W and every x in V. Probably it is reasonable to mark these neighborhoods by the point by which they are constructed. So let me write this way. And here also I mark it by the point x0, gamma 0. So in this way we obtain some family of pairs of neighborhoods. And of course, these first elements of this pair, they cover the set K. This set contains x0. So when x0 runs over all of K, then so anyway, the sets cover all of K, sure. So there is a finite number of the sets which cover K, and for them we have their counterparts, the sets W, and all of them are open. All of them are open neighborhoods of gamma 0. So let's intersect these counterparts. Okay. So we shall obtain some family V1, say N, and some set W tilde, which is the intersection of these counterparts of these neighborhoods. And what do we have? We have the following, that if gamma is in this W tilde, and X is in K, then we still have this inequality. We still have this inequality. And okay. Okay, from this follows that if this inequality is valid for all x and k for some point gamma, then it is valid for all x and k for some nearby gammas, and so indeed this set is open. Well, should I have a break right now? Or I don't simply. When does this hour finish? 15 minutes. So we have some 5 minutes. Yes. Okay, so maybe this is a logical point. So let's break. Let's make a break right now, and then I'll continue in 10 minutes.